Without further ado, let's get started with microservice architecture with Mason Jones from Credit Karma. There you go.
All right, thank you very much. I can hear myself. Hopefully that means everybody else can hear me too. My first time doing a high-tech private talk like this. It's very interesting. So, as you can see, I'm here to talk about microservices architecture in the real world. And the genesis of this talk was that as we were starting down the road towards microservices architecture at Credit Karma, we naturally did our research, looked around at what other people had done, and what we found was really success stories, which is not too surprising, right? We found information about how people had made their move to microservices architectures, what they had done and what had worked. But what was missing was all the bumps along the way, all of the hard questions that they had to think about as they were working out their solution. So I put together this talk based on the last couple of years at Credit Karma and how we moved from a monolith to microservices. This being Redis Conf, there are obligatory Redis references throughout the talk, but it's not a specifically Redis talk. A little bit about Credit Karma first. We are kind of a mission-driven company. We champion financial progress for everybody by helping people understand their financial situation and pointing them to ways to improve it. We are a little over 900 employees, close to 1,000 employees these days, about half engineering, serving over 90 million members through our native apps, web app, and so forth. And we are now doing that with our old monolith, and I'll mention that it's a PHP monolith just to have your sympathies. We now have over 100 microservices. We started out with none a couple of years ago when we started down this path. So a little bit of audience participation here first. Who here is just thinking about starting to implement microservices? This proves to me that you can hear me too, which is good. All right, and how many people here have started down the path towards microservices, but you don't consider your journey to be done? Not surprising. And is there anyone here who's already done this and you're kind of just here to laugh along with us? A couple, all right. Great. So most of you are either starting to think about microservices or have started down this path already. And congratulations are in order. It's going to be fun, it's going to be a challenge, it's going to be a lot of work, but it's going to be worthwhile. But there are going to be days when you feel like this, where you've opened this box and you didn't find what you expected inside that box. And that'll happen over and over and over. Now that you're started down the microservices path, you've got a lot of new things to think about, and these sort of form the agenda for the talk, and hopefully I will make it through all of these parts. We'll talk about routing, which is the seemingly simple question of how does a request get from one service to another. We will talk about management of these services and containers, because I'll sort of assume that if you're doing microservices, you're most likely doing it with Docker, but not necessarily. The all-important observability question of how do you look at what's going on and understand what's happening in your system as it gets more complex. And then user experience, where in this case, users are your developers, the people who are going to be impacted greatly by a move to microservices. There are lots of other things to think about along the way as well, but with limited time, we'll try to get through these. So first, when you think about microservices, you're going to imagine your system, and it's going to look something like this. It's going to be some nice looking services, talking to other services, maybe talking to some other services. And that's pretty easy. You can understand it, hold this picture in your head, see what's going on. In reality, it's going to look more like this. And this is actually only 14 services. It's not very many. Multiply this by 10 to 140 services, and it's pretty clear that you're not going to be able to easily understand what this looks like. You can't hold this picture in your head and see what's talking to what and what does it all mean. So why would we do this to ourselves is a whole other talk, but for us at Credit Karma, when we started down the road towards microservices, the idea was to improve our agility on the engineering side. As we had over several hundred engineers working on a single PHP monolith, you can imagine that trying to release twice a week was a challenge. Every release was hundreds of commits. If one of those went wrong, we had to roll back, unwind it all, and figure out what was going on. We really wanted teams to be independent, move at their own speed, deploy whenever they want, make their changes whenever they want, and not be tied to each other that way. We also got the advantage of system flexibility. You can map your services and set up your services to really fit the system that you want to have much more easily when you've got many moving parts rather than one massive part that you really can't do much with. And then lastly, you do get the option to choose more technologies. When we had a PHP monolith, our developers worked in PHP, right? It's kind of their only choice. As we started to move towards microservices, we opened it up. Teams started implementing in Scala and then in Node. And interestingly, as soon as we offered the option to write services in Scala, we did not have a single team continue working in PHP. So let's jump into the first topic of routing. And you look at the question of how does service A make a request to service B, and it seems pretty straightforward, right? Whether it's REST, whether it's RPC, it sends a request, it gets a response back, and everything is good. But it's actually not quite that easy. Service A wants to talk to service B. Great. Where are the instances of service B running? How does A get a request to an instance of service B? Which instances are healthy and are some of them unhealthy? And what does healthy mean, which is different for every different service? So you start to look at tools or other options for finding these things that you want to send a request to. Generally, a service registry is the first piece that you reach for. Essentially a specialized database that holds information about all the services that you've got and where are they. Hopefully the registry also does health checks to help you know which instances are responding well, which ones are healthy and which ones aren't. Console is probably the most common service registry you'll come across. There's also Zookeeper, or if you end up running in an orchestration system like Kubernetes, it sort of takes care of the problem for you. But Console will store where all your services are. It will do health checks that you define, and it'll help you understand which instances are working and which ones aren't. There are some other options. They're just not as flexible. You can use DNS, of course. This is to some extent what DNS was created for, right? But it doesn't really solve the problem for services all that well. Number one, DNS will return an IP address, but by default it won't return a port number. You can do SRV or service records, which will return a port number, but they're just not typically used very often. Also, DNS is not fast to respond to changes. It doesn't give you health checks, so unless you figure that out separately and change the DNS registration when something goes wrong, it's not really going to respond very well for you. And lastly, clients have a really annoying tendency to cache DNS lookups and not pay attention when something changes. You can also go simple, which is not a bad way to start, by simply deploying an instance of a service on a compute instance. If you're in AWS, you use a small EC2 instance, you deploy one service instance on it, and that's how you scale. It'll work, and it's not a bad way to get started if you need something simple, but it's not going to be very efficient, it's not going to be very fast. If you need to spin up a new instance of a service, you're going to just start an EC2 instance, wait for that, and things are just not going to move quickly. You don't have the dynamic capabilities that you get with something like a service registry. So, with the idea of a service registry, you can then start to do things like load balancing, routing, and things like that. There's an interesting project that I wanted to point people to. If you've got Redis already in your infrastructure, you can take a look at Hydra, which is a node package that provides service discovery, route discovery. It tosses in pub sub messaging just for free because Redis does that so easily. It'll do the load balancing for you. So if you already have Redis, which if you're here, you probably do, this might be a way for you to get something in place that could start you down the path of being able to register services and find them. And the link is here, hydramicroservice.com. So you know where service instances are because they're in your registry. So now you need to decide which one to send a request to. That's the load balancing. You need to decide when you send a request, how long you're going to give it to respond. You need to manage the timeouts. You need to think about whether you retry and how many times you retry if you send a request and it fails. And you need to decide when to just circuit break that service and decide, you know what, the team did a bad deploy, something went wrong, that service is just not happy. This all falls under the category of defensive programming, which when you're moving a team from working on a monolith to microservices is a really important thing to start driving home early. When teams are working in a monolith, you're very accustomed to just having code that calls some other code, and of course that other code is there. We're all in the code base together. It's going to be there, it's going to respond. Sure, there might be a bug, but in general, what you need as a dependency is there and available. Now, moving into microservices, you need to really be defensive about it and do your coding as if you know that the thing you depend on is sometimes not going to be there. And think about when that happens, when this other service that you're depending on is not available or is not happy or is responding too slowly, how can you still do the best you can? How can you give your end users the best experience possible when part of your system is out to lunch? It will happen. It's not an if, but a when. And you need to think about how can you potentially serve part of a page, but not the rest of the page? How can you provide some deprecated functionality, but something better than just an infinite timeout where the user's browser never returns? You need to really start thinking about that because it's a very different world than everything being in one place in a monolith. As an example of one of the things that you might want to think about is rate limiting. You've got a service receiving traffic from a bunch of other services. When does that service get overloaded? What do you do to prevent that service from getting overloaded? Typically, rate limiting is one option. You limit the number of requests in a certain period of time, potentially based on user to prevent DDoSing or something like that, potentially based on the client service that's calling it. Regardless of which way you want to do it, Redis is actually one of the most common ways of managing rate limiting that I've seen. It just works very, very quickly, of course, and really nicely for this. You set a key based on the user or based on a client service, whatever granularity you might want. You increment the key. You set an expire so that if you're doing it per user, for example, you don't keep the key around forever because users don't browse forever. And it's an easy way to keep track of how many times is this service being called in a certain period of time, and should you simply stop responding to requests, send an alert, however you might want to handle it. The Redis Labs site, actually under best practices, has a nice example of this that you can take a look at. So all of this complicated logic around finding an instance of the service that I want to call and deciding which one to call and handling timeouts and all of this is a fair amount of business logic. And there are two places typically where you'll see that handled. One is on the client side, and then more recently, the service mesh approach is being adopted. So the client side is pretty straightforward. Service A has all the logic necessary to talk to a service registry, do the load balancing, send the request, handle timeouts, retries, and so forth. It's all built into Service A as the client. In the service mesh approach, we take all that logic and we extract it into what we call a sidecar. The mesh runs alongside every service instance in your architecture, and it's the mesh instances that talk to each other. The services don't actually talk to each other directly. Service A wants to send a request to Service B. That request actually goes through the mesh. The mesh is talking to the service registry. It knows where things are. It knows what's healthy. And it makes sure that the request gets to the right place, which is the mesh instance alongside the instance of Service B that you want the request to go to. Like everything, there are pros and cons to both of these approaches. For the client-side approach, it is simpler. You know the code is there. It's in your service. It's doing its job. But you've got the normal client library management problem. You're going to be updating this client-side library. You're going to need to be updating then every single service that's using it. If you've got even 20 services, 5 instances each, that's 100 instances, 100 containers out there with this client library built in. If you're upgrading your library, you need to somehow get everybody who owns those services to upgrade, redeploy, and get the change out there. And then if you want to take advantage of teams being able to work in different languages, suddenly you're supporting this client library in every single language, maintaining feature parity, upgrades, and so forth. And it's a non-trivial maintenance overhead. So the service mesh is more recent and is what people are really gravitating towards. You don't have any libraries to maintain. It's a separate thing that runs alongside your services. You get automatic observability out of it. The service mesh technologies out there all send out metrics, send out logs. They help you understand what's going on, which services are talking to what, how latency is going, and so forth. You also get security. You can do MTLS between service mesh instances and get additional security kind of for free. But the main disadvantage is that this is another complicated piece that you're adding to your infrastructure. Your service mesh becomes absolutely critical of if or when anything goes wrong with it, your entire system is impacted. So if you do the service mesh approach, I strongly encourage you to dedicate a team to owning it, learning it inside and out, and be able to take care of it when something goes wrong. So out of all this, what's the right answer? Like all of these complicated things, it depends. If you're just starting out, I would certainly recommend taking a look at Console as your service registry, or as I said, if you've got Redis, take a look at Hydra. That might be a way for you to get started fairly easily. When you start to look at managing all of this logic, service meshes are very new. The best known one, Istio, is only version 1.1. It's barely production ready. It's very, very worth taking a look at, but be cautious. As I said, it becomes a core part of your system. At Credit Karma, we started down this road before Istio was really out there. We've been using a service mesh called Linkerd, which has been doing the job well for us. But it's definitely taken a fair amount of time to get comfortable with it, make it reliable, and really understand how it runs. Jumping into management of all of your services. So when you're depending on where you're at now, you're probably not running tons of services on tons of servers. You're probably not really worried about managing your resources super efficiently, dealing with dynamic cloud instances coming and going, auto-scaling, and some of those more complicated things. You're just getting started. So assuming that you don't really need to worry about these things today, my first biggest advice is to not dive into too many new tools all at once. It's very easy to kind of look at all of the fun stuff that's out there, really, and say, all right, let's bring in Docker, and let's bring in Kubernetes, and let's bring in a service mesh, Istio, and let's bring in all of this other stuff. And suddenly, you're 9 months down the line working on this project, and you haven't deployed a service yet because you're still figuring it out. And you don't really know what you're going to need yet. Every company's microservices architecture is a different shape, has different criteria for success. Some companies really care about performance. Some companies care more about plain old stability. They don't want to do anything too fancy. So use the tools that you know. When we first started out, we had no services. So we took some servers in our data center, we installed Docker on them, and we got some practice running Docker in production, and some practice fixing Docker in production and debugging Docker in production, because it didn't really work perfectly on day one. Then, once we had a service running in Docker, we brought in Console for service discovery, and then we could start to kind of make things a little bit more dynamic, but we were still managing things very much manually. We did not have an orchestration system. We were running, honestly, Supervisor to make sure that the Docker processes were kept running. But it worked. We knew how it was supposed to run. We could make it work. So automate things early on, but also plan ahead. What got us was that the first couple of services were slow to get going. We had some teams that were guinea pigs for us. They were pretty happy to work with us to get it going. And then the next couple of services were a little bit faster, and then suddenly every team wanted to run a service, and we turned around and we had 20 services running already, and we didn't have the tooling to do it very well. We were trying to keep ahead of the demand, and we wanted it to work well because we wanted teams to adopt services, and if they had a bad experience, then we were going to lose them, and it was going to be hard to talk them into services again. So plan ahead, watch how the momentum is building, and get ahead of it. Start researching the solution to your next step as early as you can. So we turned around one day and realized, oh, we have too many services. We're managing this manually. Our orchestration was a Google spreadsheet listing servers and what services were on them and what port, honestly. But it got us going. So clearly it was time for a framework, for a tool to manage this for us. There are lots of options for orchestration these days. Kubernetes is obviously top of mind for everybody. There's Docker Swarm. If you're using Docker Compose and you like it and you want to run Docker Swarm, you could try that. There's Nomad from HashiCorp, the same company that provides Console. Nomad doesn't have as many features as the others, but it's small, simple, fast, easy to use. Depending on your needs, it might actually do the job very well. Mesos and Marathon, to be honest, have not really been keeping up with state-of-the-art for container management. But if you're running DCOS in your data center, you've got them already. You could just try them out. If you're in AWS, you've got ECS. You could run Fargate. ECS is, honestly, its own oddity. It works well. It could be a way for you to get things going pretty quickly. But Amazon has managed Kubernetes now for a reason. So Kubernetes is really the clear winner in the orchestration space at this point. It's very difficult to recommend anything else at this time, despite the fact that Kubernetes has quite a learning curve. Now that you've got managed Kubernetes on every cloud, it's even easier to recommend. Kubernetes has a lot of primitives that just match the way microservices architectures commonly run that make life very, very easy. They've got objects for services for deployments. You run your service in a pod. A pod is essentially like a mini VM where you can run a bunch of containers next to each other as if they're on the same host. You can run your service mesh sidecar in the pod with your service. That's typically how it's done. You can also run something like a Redis cache in a pod next to your service. When you start a new instance of your service, it starts up an instance of Redis right next to it. So you've got your cache just right there, easy to run. Namespaces for separating services, node pools for separating hosts, access control, a lot of things right out of the box. You've also got tools like Helm now, which are essentially a package manager for containers, for services. So if you want to run Redis in Kubernetes, you grab the Helm chart for Redis, you run it, you've got Redis going. It's really, really easy. So with the managed Kubernetes and all of these tools now, it is much, much easier than it was a couple of years ago to get things going, thankfully. Jumping into the all-important observability. Once you've got these services going, your developers are going to be coming along with tons of questions. It's not as easy to see what's going on anymore. They're going to have questions, and you're going to have questions, like what services are healthy and what's not, and why? Why is my service slow and someone else's service isn't slow? Why is my service slow sometimes but not always? Why is it slow for some customers and not others? Why are my requests sometimes timing out, but sometimes they're fine? Why is this service sometimes spiking the CPU and other times it's running perfectly well, and so on and so on. With a monolith, there were a lot fewer questions, really. Not to oversimplify it, but in a typical monolithic architecture, you've got a load balancer, you've got instances of your monolith, and you've got a database. The monolith may be a total mess inside it, but from a system perspective, you've got many, many fewer moving parts. It's simply easier to understand the system and what's going on. So you figure, all right, let's start collecting metrics, see what's going on out there. But those might really not help as much as you expect. If you've even got 20 or 30 services and you've got maybe 5 instances of each service, that's 100 to 150 containers running out there, all emitting metrics that you're collecting, and you're trying to make sense of it. And it's just not that easy. You can't simply start pulling metrics into your time series database, whether it's Redis or something else, and understand what's going on. Which metrics are you going to care about? You're probably going to look at your container CPU and memory for all 100 to 150 containers and see what's going on. And then you want to get the host CPU and memory as well, of course, so you understand, maybe correlate this, this service is not happy, and that's because the host is unhappy. And then you want to collect the disk and the network usage, and maybe one of the containers on the host is hogging all the network, so all the other services on there aren't able to do their jobs. And then you've got the request latency for every service, and actually every instance of every service. So again, that's another 100 to 150 metrics. And then you've got the service metrics, because each service is supposed to do something that you care about. And you can see where this is going. It's just too much information. You can't make sense of that, and your dashboards look like this. And unless you're in the matrix, who knows? Who knows what that means? So step back and think about why you care and what you care about. The example I like to use is if you've got this service over here and it's spiking the CPU sporadically and you really can't figure out what's going on, but your top level metrics for your site show that your users are getting their work done and they're happy and all the traffic is flowing, do you actually care that that service is spiking the CPU? You sort of don't. You care a little bit because you should probably look into it because something is not quite right, but it's nothing to alert someone at 3 a.m. about. It's just not that important because your top level metrics are actually showing that things are working okay for your users, and that's what you built the thing for. So make sure that you can answer the important questions when something really, really critical happens, but don't get overwhelmed and start collecting every single metric in the world just because you can. You're going to be collecting a lot of information. You've got logs coming from any number of tools. You've got metrics coming from any number of tools as well. Distributed tracing is one that I'll specifically call out, though, because it's specifically important in the microservices world. Distributed tracing using Zipkin, OpenTracing, Jaeger, or any of these tools is essentially like a stack trace for your services. You've got service A calling B, calling C, calling D, and you essentially inject a transaction ID at the very top, flow it through, and stitch the spans together to understand what the stack looks like. That gives you an idea of the flow. It tells you who's calling what. It tells you which ones are sending more errors than normal. It tells you which ones are slower than normal. It can help you identify that a new deployment of a particular service is now having an outsized effect on your system because that latency is growing and everything above it is suffering because of that. Without something like distributed tracing, it's really difficult to figure that sort of thing out. So again, think about what signal you care about and try to either not collect the noise or at least put it aside in the extremely rare event that you care about it. Think about who is going to be looking at the parts of your system, what information they're going to care about from time to time, when are they going to need that information, and then make sure it's available to them. Lastly, user experience, where again, I'm talking about users being your developers, and this is an often forgotten piece of moving to microservices. You want your users to be happy. You want your developers to look like this. They're happily coding away. And you need to understand, how do they work now with a monolithic code base? And what is it going to mean to them when you start to pull that apart into lots of new pieces? As an example, everybody always kind of wants their development environments, their test environments, their production environments to be the same, right? Because then you do your testing on your laptop and you can feel confident that when it goes to your QA environment, it's going to work, and when it goes to production, it's going to work. With a monolith, that's still hard, but it is achievable. But now, moving to microservices, you're throwing in all of these new pieces, all of these new things to deal with. You're running Docker in production now. So do you run Docker for Mac and try to control the versions and make sure that they're the same everywhere? You're running Kubernetes in production, maybe. Does that mean that you need to run Kubernetes on a laptop? Maybe. It depends on how important you think parity is. You're collecting logs and metrics, and you want to make sure that those are going to work when a service goes out to test and out to production. So do you run those on a laptop? You've got service discovery like Consul. Well, if Consul is how services are talking to each other, then you need that on a laptop and in a QA environment and so forth. And now, if your system grows to 100 services, it's not going to fit on a laptop anymore. We hit that fairly early on, where it's just too much for a MacBook to run, even now that Apple finally gave us more RAM on them. The bad news is nobody has really solved this perfectly. At least nobody I've talked to. If anyone out there has, please talk to me afterwards. I'd love to hear your story. There are a few fairly common approaches. The main one is a shared cloud environment. You have your staging environment. Everybody deploys the latest version of their service out there, and that's where you run things against from your laptop. I'm a developer doing my work on my service, and it relies on several other services that another team owns. I just talk to those instances in the shared dev cloud. That can work. It's got some shortcomings. Among other things, if you've got a couple of services that are very heavily used, which is pretty common, if the team deploys a bad version of that into your staging environment, suddenly every single developer is dead in the water. It's almost like supporting another production environment, because it has to be there or nobody can really do their testing and do their work. You could go with mock services. We've played with that idea. Problem with mock services is, of course, they're mock. They don't really behave like a real service. They're not going to have the full data set. They're just not going to be very satisfying, honestly. The last approach is one that we have played with for a while, and it's sort of working, but it's really not going to last all that long, is saying, all right, I'm a developer working on my laptop on my service, and it depends on 5 other services, but actually doesn't care about any of the others. So automate the process of saying that I need to work on my service, I know what its dependencies are, and my dev tooling will automatically ensure that those dependencies are up and running on my laptop and ignore everything else that I don't care about. That's surprisingly hard to do because mapping the dependencies is surprisingly hard to do. If you've got 100 microservices, identifying one of them and saying, which services does this one depend on to run, is a tree. Because it'll depend on some that will then depend on some, and tracking that is really not easy, as it turns out. So like I said, nobody's solved this perfectly. I think the shared cloud is really the best of a not totally satisfactory set of options. And this ties into the fact that tools integration is really, really hard when you're moving from monolith to microservices. Too often, we look at going to microservices and we focus on production, which is natural. We want production to be solid and stable, and we want it to run well. We want all of the tools to work there, but there's a lot that happens before code gets to production. And it's really, really critical to any engineering department operating properly. You've got development tools that your engineers are working with, IDEs, debuggers, and so forth. Well, trying to get those to run in a containerized world is not as easy as it might be so far. You've got your build and CI tools, of course. Well, they're building a monolith, they're testing a monolith. Now you're suddenly looking at how do we build and create a test environment with a whole bunch of services that are going to operate properly, and do we know which version of every service we want to test against at any given time. You've got your deployment tools for deploying a monolith. You're going to have to figure out what deployment tools look like for deploying services now. Our whole idea was giving teams independence, letting them deploy whenever they want. Some teams deploy once a month. Some services kind of reach a stable point and they don't change very much. Other teams are deploying their services 10, 20 times a day. That's totally fine, but the tooling needs to be there to really make it work well. Then logging and monitoring, fairly obviously, you've got logs, you've got metrics and so forth coming out of your monolith. You're going to need to figure out how to get logs out of your containers into Splunk or whatever logging tool you use. You need to figure out how to metrics get out of your containers, out of your orchestration system, whatever you put in place, so that you know what's going on. So there's a lot to the process before you even get to production that you really need to think about. So there are a lot of changes involved, more changes than you would expect. But it really is very worthwhile. We've been very, very happy with the results of making this shift. It's forced us to put a lot of effort into stability of the tools, of the frameworks, of the infrastructure. It's forced us to really revisit our whole development process, but the outcome has been the efficiency that we wanted and the ability for teams to work independently that we were after. So it seems like a lot, and it is, and talking about whether microservices make sense to you or not is a whole separate talk, but it can pay off. Thank you very much.
So looks like we got a couple questions.
Excellent.
Thanks for your presentation. You did present a very complex topic in a very simple way. It's not an easy job.
I hope so.
Yeah. And my question is, when you went from monolithic to so many services, what have you done for database? I mean, how do you share? How does this each services share the data?
Yeah.
Through REST APIs, or they have individual data stores? That's the question.
We have stuck very, very closely with the restriction of one database to one code base. So every service has its own database. We never have a database written to or read from by more than one service, because that's just another coupling that makes your database into another monolith in a sense, and it obviously means that one team couldn't make a schema change without impacting the other team. We wanted to avoid that. So when we started rolling out services, we said, if the service needs a database, which most of them do, then we provide that service with its own database. We run a very large MySQL cluster, and we just create new logical databases within the physical cluster for each service to give the data isolation, but not increase the load on our DBAs so that they're maintaining 120 different databases. And another thing is we do not containerize our databases. We're running a MySQL cluster on bare metal, not within Docker, not within Kubernetes.
Hey, thanks for a great talk. I'm just curious, you mentioned that your teams are now split between using Scala and Node.js. Out of curiosity, what percentage are using Scala, what percentage are using Node.js?
The Node support is newer, so that skews the numbers. I'd say at this point, I think we actually have two PHP services from the old days, from the original set, and it's probably still about 85% Scala and only 15% or so Node, just because it is newer. I see Node picking up speed, so I actually have a feeling that those numbers are slowly going to flip, and I think we're going to end up with more services in Node, partly just because TypeScript is a more common language these days, the full stack language idea, and Scala really has quite a learning curve. I'm personally voting for adding Go to the set, so we'll see if I can get my way.
Use change management to manage your shared cloud?
So our shared cloud right now is very small. We have not moved to really having a full shared cloud for development. So right now we don't have any particular change management. Again, we want the teams to kind of move at their own pace. So we're to some extent relying on the testing process to say you do your unit testing on your laptop, you run through the build pipeline to build your container, and that runs integration tests, and then if those pass, then it should be good enough to put into the shared cloud so that everybody else can start operating against your next version. The trick is, though, that the version of a service that's running in that shared dev environment is probably going to be somewhat newer than what's in production. So if a team is trying to debug a problem in production, they don't necessarily have an easy place where they can test against exactly what versions of everything are in production to try to reproduce the problem. So then, do you have yet another environment in between, and how many environments can we manage? So it's a tricky set of problems.
Hey, thanks for the excellent presentation. It was amazing. One area was somehow omitted in your talk.
Several.
Yeah, but one it's quite important. What's Credit Karma approach to testing? Do you have journey testing between microservices? How you organize all this stuff? Thank you.
Yeah, the testing is worthy of a whole talk on its own for sure. Number one, we, again, in the spirit of teams owning their own destiny, teams themselves are responsible for the tests for their services. If a team wants to shortcut the tests and take some risks, that's going to be okay unless they start to have too many production problems, in which case someone is going to go and have a talk with them. But how much testing is enough is something that we really feel is the responsibility of the teams themselves. So that will flow from the unit tests that they do early on their laptops into integration tests. We have a central build pipeline that all of the containers, all the Docker images are built through, and that's partly for security reasons and compliance reasons, as well as just maintaining a known pipeline that's reliable. That includes running tests as part of that pipeline so that the image that comes out is smoke tested, but then teams are expected to take the image that comes out of that, pull it into an integration environment. We are now running in Kubernetes primarily. Not everything is in it. So what we've built is what we call DevCube, which is the ability to bring up a single cloud compute instance with kind of a tiny Kubernetes on it with the full set of services. So because it's in the cloud, we can scale it larger than a laptop could do, so we're able to actually bring up a replica of production with all of the services available, and then they can run through their integration tests. And typically that's a matter of verifying that all their endpoints are responding appropriately and so on. But we did have to kind of put that together, and how rigorously they test all of the edge cases and so forth, again, is really up to them. Ultimately, they're the ones who will be paged in the middle of the night if their service is suffering, so they're a little bit incentivized to make sure their tests are good enough.
Thank you for the great presentation. It's really nice to see the problems you had. So the question I had is, how did you guys manage configuration for each service, especially the deployment, right? When you change, because each service may have hundreds of instances, so how did you change the config service at runtime?
So configuration settings for our services start out in a file in their Git repository. And as part of our build pipeline, we actually pull all of those settings out. We push some of them into a Helm chart for the service. We push others into console. We actually use console's key value store for configuration settings for the services. So when they, how to talk through it simply, when the build is done, the configuration file flows along with the image into a repository that we keep. Then when the new version of the service is deployed, our deployment tool actually picks up that information and pushes it into console as part of the deploy. And every build of an image is versioned. We do semver plus a timestamp. That versioning is also used in the console tree in the key value store, so that every deployment of a new version has its own new configuration settings. So if we need to roll back, we don't have an old version of the service trying to run against the new configuration settings, which is usually going to be trouble. So that's kind of how we manage the configurations going out with the services.
Thanks for the extensive demonstration and talk. I had a question regarding the security of your services. So how do you store passwords, secret keys, and other things? Do you use a secure vault for that, or what exactly do you do?
We use HashiCorp Vault, yeah. And similar to how the configuration settings get deployed with the service, some secrets will get deployed with the new version of the service. Most of them, though, are done out of band because, again, we can't have secrets in source control, so they have to be stored somewhere. But in some cases, they'll be already in Vault, and they can be copied over to an appropriate place. Yeah, the security is a whole, again, separate talk. That was the first thing that we thought about when we were starting to deal with microservices. The main question being, are we comfortable with a developer building a Docker image on their laptop, pushing it to the registry, and then deploying it to production? No. So we had to build the whole pipeline to manage that and track things for compliance and everything else. And we are counting down to 0 here.
That's all the time we have, so thank you, everybody.
Thank you very much.